And so here we go. We can see where we have a larger population density pretty easily. So this is kind of interesting. Like there's not very many people in these areas. Like this one I find very interesting. You know, since it's such a high population density, then no one over here. It'd be, you know, interesting to look at why. Probably has to do with like the history of the history of the city. Okay, so now what we want to take a look at is what do I do when I have multiple polygons or multiple spatial data sets that I'm working with, and what can I do? So here we're going to look at geometry union, and so what we're going to do, we're going to take two geometries, put them together into one spatial polygon. All right, so here I'm taking all the polygons from this and I'm putting it into one big polygon. So all of the little polygons that we saw a moment ago with the different colors of yellow and red are now just going to be one big region. And let's compute that area. And we can see that's much larger than the other areas we had previously because it's all of them put together. All right, now let's go ahead and get the area of the polygons. And you'll notice what ends up happening is that I've got one big one, then all of these are within machine accuracy of 0. So there's just, meaningfully, there's just one polygon going on. So let's go ahead and plot that. And we can see these little specks here. These are probably like holes in the data set, holes in the geometry, maybe some lines, something like that. And that accounts for these little tiny numbers that are off by themselves. So here's what, there's 6 of them. So 1, 2, 3, 4, 5, 6, boom, we got it. Now we're going to test to see if the geometries overlap. Okay, so this function, the G overlaps, checks to see, do we have any geometries overlapping each other, on top of each other? This is important to know because if I start plotting them, I want to know, is one blocking the other on my map? Now, when I look here, we know that these guys are on top of the big one. Therefore, we know it's going to be true. And boom, we got it. All right, so let's go ahead and set our scale. And we're going to do our overlap. And now, notice that I've reduced the scale by quite a bit since I've reduced my precision. Now, when I run the overlaps function, I get false. So I'm not seeing any overlaps on this scale anymore because those other ones were so tiny that they wouldn't even be detected. And now here, what we're doing the same thing to a large extent. Is so the O scale a moment ago was the default scale that I had set. So I saved it before I changed the scale. Now I'm changing it back. And here I can get my area. The lesser precision scale could have resulted in a less accurate number here. And now the upcoming code is going to probably throw some warnings. So the author went ahead and put it to false for the warnings. So now let's read in some more data. All right, this time we're going to use the L7ETM8S TIFF file. And we can see that we have 704 rows, 698 columns. And it's griping about the projection. So let's go ahead and set it to the one that we want. So what I'm going to do, I'm going to take the object I'm going to be working with. I want everything to have the same projection. So instead of like figuring out what it is, I'm extracting it. I extract the projection. I set that to the projection I want, and I say that's the projection for the object I'm going to be working with. Easy peasy lemon squeezy. Now let's load another data set. This is L7 ETM's TIFF, and we're going to call this TM. The previous one we called PAN. And I'm using the same trick to define the projection string. So I'm taking the object whose coordinates I want to use. I grab its projection string. I set the coordinate reference system to be the projection string of the object I want to work with. And let's go ahead and get the names of our TM objects. And this is going to be TM1, TM2, 3, 4, 5, 6, 7. I believe these might be principal components or something like that. One of the data sets of principal components. I don't know if this one doesn't really matter what it is, where it came from for our purpose, because we're just trying to look at how to handle geographic data. And then here, let's load some more data. So this is Olinda DIM, demographic information, UTM 25S TIFF. 11 rows, 11 columns. Now, something that should be jumping out at you is like, hey, we have different rows, different columns. How are we going to combine that? You're going to find out soon. And once again, I'm going to set the projection string exactly the same way I did with the previous two. All right, so now what I'm going to do is whenever we have a missing value, so I'm going to take the values that don't make sense. So it's less than or equal to 0, which doesn't make sense for this type of data. I'm going to say, hey, that is a missing value instead. So this is an unusual way of defining missing value. And now let's go ahead and plot our TM objects. And so we get to take an interesting look at the Olinda city. Now, remember, these are default colors. These are default colors to go, from yellow to dark. There's, this color palette is pretty good for the purpose of like people who are colorblind. It's also good that, the bright is on one scale, dark is on the other, and color of the rainbow goes along the scale also. So people will actually do a better job judging what they're looking at, but these are definitely unnatural colors to be looking at. I wouldn't use these professionally. I've definitely use these while I'm working on it, but before I give it to my stakeholders, I would choose a different color palette to be more informative with what we're looking at. Now here we have DIM. We plot that. So here you can see that we have, a map going on, and we've got some missing values in here. And we can see that there's some missing values in this also. Now we're going to turn on that warning again. And then the author turns it off. Don't know why. Now this upcoming chunk of code, I wasn't able to find this file anywhere, so I just skipped over this code. This chunk was not ran, but here is the SP Grass 6 package to work with. And it looks like it's got some utility to it, but without the file, I don't know what to do. So I just skipped it. All right, so now let's go ahead and load some stream data. So let's get the shape file for streams in Olinda. I'm using rgdoll package, read OGR. And it's going to be a spatial lines data frame. We're going to represent the streams, the water, with spatial lines. Now I'm going to go ahead and set the projection. And now let's go ahead and plot it. And so now we can see cat, value, and label. And we can also see where are the streams in the city. So we can look at the number of rows in there. So we can see how many streams we're talking about. get summary statistics of our data. Now, next thing we want to ask ourselves, when I'm looking at two spatial data sets, do they touch? Is there any connection between them? Are they completely separate? Not only are we interested in like overlaps, we're also interested in, do they connect? Is it going to be like Florida and Georgia where they do connect, or like Florida and New York State where they don't? Okay, so we're going to use the G touches to check to see, do they touch? Now remember, scale can change the answer on this for yes and no. If I have a coarse enough value, I can get true. If I go super fine, it's possible to get false on the same data sets. So be mindful of that when you set your scale. So next we want to convert a square spatial matrix to a weights list object. And to do that, we're going to use matrix to list W. So we're taking a matrix, converting it to list weights, weighted list. And so I'm taking the GTouch streams outputs that we have here. So the output here is going to be a matrix indicating if two polygons touch, yes or no. And then this is converting it to that weighted list. And now here we can go through and we can look for searching neighbors by going by which ones touch, which ones don't. And so here we see that we can have the, we got 21 like connecting neighbors. Now, next one that we want to look at is another union, but this time we're doing it on lines. We're not doing it on polygons, we're doing it on lines that we want to put them together. So I'm going to take that spatial lines data frame, and I want to merge them all into just like one big body of water. I'm going to use G-line merge to do that. And we see that we end up getting 21 distinct streams. And we can get our summary statistics off of that also. And you'll notice that our spatial lines length is equal to what we get off of that G length computation. And so now let's go ahead and plot it. And so we can see that we have some individual streams here and there. Now these are all connected, then merged into just one big stream. So we don't know, like we can't figure out the direction necessarily. You know, we know where the ocean is, so we probably could work out some details. But so we can see the distinct bodies of water that don't connect to each other off of this map. Now, next thing we want to take a look at is geometry intersections. So if I have two different geometries, maybe I'm interested only in where they overlap with each other. And to do that, we're going to use G intersection. Kind of G, then whatever operation I want is the convention in rgeos. It's kind of nice. And so I need two sets to be able to do the intersection. So I'll do spatial line stream and spatial polygons data frame for the Olinda with the second projection on there. And we can see that when I do this, so what I'm doing is I'm taking polygons and I'm taking lines, I'm taking the intersection, I end up getting lines. All right, so as you do this kind of thing, you know, if I had polygons and polygons, it's possible that if they overlap like this, I get that middle polygon. If I have polygons and their borders intersect, then I'll get a line, or if they only touch, I could get a point. So when I do this, different polygons or different spatial objects mixed together will give me different classes of geometric objects. And so on this one, we get spatial lines because I'm taking lines that are really contained for the most part, maybe not necessarily, but a good portion of them are contained inside the other polygon data set. And so now let's take a look All right, so that's how many of the original streams are left after the intersection. And let's go ahead and plot it. And notice that I'm using regular plot on this one. I wasn't able to get SP plot to work with this, so the colors didn't come out. And so this is what's left after I take the intersection with the polygons. And this is just demonstrating aspects of like the number of rows, the information that we have on each stream. And here, we can compute the lengths of our spatial lines. And something that we can do, we can use tapply, that I'm taking those lengths, I'm taking the index from the intersection on the streams, and I'm adding them up. And so then I ultimately get some new information about those combined bodies of water. All right, so now here are some experimental functions that are in rgeos. So G unary str tree query and G binary str tree query build input envelopes by disregarding topology and reducing the coordinates to a multi-point representation. Okay, so these build envelopes by ignoring the topology structure that's already established, and then reduces the coordinates to multi-points. And so this permits the trees to be built and queried even when some geometries are not valid. And so if you want, you can dig into these. I haven't used these professionally, so I don't really have much to say about these. All right, next one, buffer geometry. So let's say I want to take objects I have and I want to put a buffer around them. Well, the gbuffer function will do that for me. So what we're going to do on this one, we're going to take our bodies of water, we're going to put, so you know that they're just lines. Well, what if I go, you know what, I'm dealing with some pretty big bodies of water. Having just a line doesn't make sense. If I've got a big river, big canal, something like that, having it as a line doesn't do it justice. It's bigger than what it looks like on the map. Well, what I can do is I can put a buffer around it so it looks wider, it looks bigger on the map, so I get a better representation of what's actually there. All right, so what we're going to do is with the gbuffer function, I'm going to put a width of 50 on there. And then when I plot it, I can see the same bodies of water, but now I've got some space between where the line was. So the lines were originally in the middle, and it just kind of put a buffer around it. So now it looks like an actual flowing river instead of a brook or a stream that I could step over. And of course, we can compute buffer area. So what I need to do is just figure out the polygons, and then I can compute it. And so we can go through and we can do some intersections. And so you'll notice that in this intersection, so even though this is inside the geographic region we're dealing with, there is a limit to the precision of our data. Because of that limit in the precision, we can see that parts of the buffer rivers that should be there are not there because there's a lack of precision in this data set here, unfortunately. And these are just like playing around, digging into what we get. So this part is working into computing the area of our buffered geometry regions. And so now we can, so I have the option of adding on to our spatial polygons data frame by just treating it like a regular old data frame. And when I plot it using SPplot, you'll notice that it gets plotted immediately for us along with the others. So now let's take a look at which streams are actually inside the city of Olinda. So those streams were taken and they're in the area of Olinda, but they're not necessarily in the city boundaries. Now I want to look at only ones that are inside the city boundaries. So we're going to do G intersection. I'm going to take the streams, and then I'm going to say do the one, grab everything that's inside that big polygon. And so when I plot it, I can see this is all of the streams that are inside the actual city limits. The other streams that are outside that we plotted previously are in the area of the city, but are not properly inside Olinda. All right, now, so let's go ahead and plot another variable that we created. This time we're going to use the Brewer palette function to just get blues, and we're going to get 5 of them. So I'm taking my spatial polygons data frame. Here is the variable from the data frame that I want. I'm saying that, so, and this color palette actually returns a function. So this is a function for returning colors. I want 20 different colors, and we're going to add transparency to the background. And then our layout is going to be a list. So this is a specialized